Hi. During my previous sessions, we covered what is the training period, the validation period. We did as well like an introduction to forecasting techniques. During this short video clip, we are going to cover smoothing forecasting, which is a method that is very interesting and that you are going to see that uses weights just instead of just the average. So it's going to give weights to the recent observations and to the oldest observations. So let's go to see how it works. Let's go to my full desktop. Right, so we are here. I think I opened twice this. Yes, and I think this figure well says everything. This is just a reminder that we are going to use weights in order to try to train our forecasting method this time. So we are going to give weights especially to the recent data and the oldest data. That is the idea of forecasting with exponential smoothing. So yes, the idea of exponential smoothing, as the name says, is to smooth. So I have this little picture of this baby because, well, among others, because I have a little baby as well. Yes, and well, she is using the makeup, yes, to smooth. Although obviously this beautiful baby doesn't need that. Anyway, so the assumption has only level and noise. So that is the assumption of the model. So I recall that a level, for instance, if we have, say, a time series, imagine that this is a y-axis and a time axis, and we have a GDP. Yes, it can be GDP here. Yes, and we have something like this. Yes, the level is the average of everything. Yes, that is the level LT, right? And the noise or the remainder is the rest. Yes. So we have that the noise is unpredictable. Yes, that is what we call it noise because there is no information there. Yes, and the level will stay put, so it is always going to be around here. Yes, the forecast equal the estimated level. Yes, in this exercise is the estimated level at most recent time point. Yes, so this F is forecasting. Yes, this T is the time of the time series. Yes, and this is the K is the number of observations that we want to forecast. So this is obviously from time 1 plus something there. So this is the future equals the level of T. Yes, this is the level of T. Yes, so we have an adaptive algorithm. Yes, so like a mathematical formula that adjusts for the most recent forecast or level, yes, based on the actual data. So that is ft, yes, which is the forecasted value in times t, equals, this is the alpha yt. So alpha is a coefficient, right? And yt is the variable, the main variable that we are using. In this case, we said that it was going to be GDP. So let's stick to GDP in times t plus 1 minus alpha. Can you see that we have 1 alpha and 1 minus alpha? Yes. This is because this is from 1 to 100%. We are going to give a weight to yt, and we are going to give a weight to the forecast in the previous period, ft minus 1. Yes, right? So that is how we are using weights, as I started this a lecture in order to forecast the future. Yes, so we give a weight to the observation in times t, yes, and a weight to the ft minus 1, yes. We have to initiate this model with f equal level equal y minus 1. Otherwise, we will not have like a number to start the model with. Yes, and also I want to mention that the alpha coefficient is going to be between 0 and 1. Yes, so between 0 and 100%. Yes, or 0 and 1. This will ensure that if this is 0.5, this term here is going to be 0.5. If this is 0.3, this is going to be 0.7. If this is 0.1, this is 0.9. If this is 0.9, this is 0.1. Yes, both of them, yes, needs to be equal to 1. Yes, because this one is alpha and this 1 minus alpha. Right? So, for instance, we have here the human population growth. Yes, from this formula, for instance, if we stand here, this could be yt. Yes, yt. And let's imagine that this is another of the previous observation, which is 1 minus alpha for the forecasted value and at ft minus 1. So this will be the forecasted value at ft minus 1, which is obviously equal to lt minus 1, I think, no? To lt, yes, so which is the level at this value, right? So that is going to ensure that we are going to have like a forecasted value around here. This one plus this one is going to give us something around here, right? So that is the idea of the exponential smoothing. Yes, to give weight to the observations. So I think we mentioned here that LT equal alpha yt plus y minus alpha LT minus 1, right? So if this is yt minus alpha, sorry, if this is alpha yt, this term, this is LT minus 1. LT minus 1 would be the level at, you know, the previous observation. And that is going to give us the forecast or the level for the particular time t. So why is it called exponential smoothing? So we have here that the formula for the level, yes, the average, that we are going to use in this algorithm, in this technique, is a coefficient alpha, which is between 0 and 1, times the observation in yt, yes, plus 1 minus alpha, which is obviously, if this is 0 to 1, this is the remainder of alpha, yes, times lt minus 1, yes. So if we have a function like this, right, and this is the level in time t, the level in times t, yes, we have an alpha yt, so the alpha yt will be this, so alpha, or this is going to be yt, right, and this is lt minus 1. Let's say that this is lt minus 1. In time t minus 1, yes. So therefore this lt, this is the level in times t, equals a coefficient that I call alpha times yt plus this previous level, 1 minus alpha, and that previous level, LT minus 1. So if we substitute the formula of LT minus 1, yes, or we can substitute LT with its own formula, yes. So we are going to substitute this part of the equation, then we will have this long equation, yes, in which, for instance, this LT minus 1 is going to be equal to LT minus 1 is going to be equal to alpha yt minus 1 plus 1 minus alpha, yes, time LT minus 2. Yes, this is what we have in here. This thing here is this thing here. And we can further make LT minus 2. Yes, and carry on doing to the infinite. We will go to LT minus 3, LT minus 4, LT, etc. Right? So, but the idea is that, and this alpha will be increasing here to the square root and to the cubed, yes, but that is not the idea, yes, I mean, at the end we will have something like this, yes, which is going to go to the infinite depending on the number of observations, and the weights will decrease exponentially into the past, as you can see from this formula, right? So, and they will decrease exponentially, as you can see, yes, they will be decreased with the alphas will decrease exponentially with these exponentials. So we do not want to do that, this long formula, yes, because it's very time consuming for any computer, yes. So another way to view of viewing it is an adaptive learning process, yes, in which we have the same formula here that we were using before, yes, for LT, the level, and what we are going to say is that ft plus 1, yes, the forecast in time t plus 1 is simply the forecast or the previous forecast plus an error term. This, guys, is equivalent to the exactly to what we have done here in all these equations. So do not worry if you did not understand quite well the mathematic part here. The main idea, guys, is that we are going to give here to the errors in alpha value, and that is going to be equivalent to the measure that we had in the previous slide. Yes. So what exponential smoothing is going to do is to update the previous forecast by an amount that depends on the error in the previous forecast. Yes. So we need to get to know in a smoothing the previous forecast and the error, yes, of that forecast, and we are going to update the values given that forecast. This alpha controls the degree of learning, and this is actually very important because here we are starting to talk about learning, yes, and because of this learning, for the very first time we can speak about robots. Yes, we are making an algorithm that learns from previous observations. So let's imagine that we have the same GDP here, yes, and imagine that this dot represents my forecast in time t plus 1. this forecast in time t plus 1 equals the forecast in times t plus alpha times the error in times t. So imagine that I do have a forecast, so I have something like this. My forecast is around here. Yes. So this is my forecast for time t. I'm going to put here t. Oh, this is times t, and this one here is t minus t plus 1. T plus 1. Yes. So my forecast in time t plus is going, my forecast in this time, or this one, is going to be this forecast plus the error. You can see that the error is this, the difference between the actual value and my forecast. So I'm going to sum up this error and this forecast in order to forecast the future. Obviously, I can increase this forecast by a factor. So this factor will like ensure that I am going to be very close to the real value in the future. And this alpha is a learning variable. Right? Okay, so the smoothing constant alpha, I think, is the most important, one of the most important parts here in this technique. Alpha determines how much weight is given to the past. Alpha equals 1 means that past observations don't have no influence over forecasts. Yes, under smoothing. Yes, so past observations no influence over forecasts. That means that the alpha, the error, is going to be 100% the previous error. And alpha equals 0 means that past observations have a large influence on forecasts. So in other words, in this one, yes, the previous observations has a strong influence. In this one, the previous observation does not have that strong influence. We will take into account like very much the oldest information. So how to select alpha just to start the algorithm? Usually we use values between 0.1 and 0.2. That is like the norm, yes. But the algorithm obviously adjusts the alpha up until find the optimum. Right? And it does that through trial and error, yes. So the idea is that we want to minimize the root mean square error. This is the root mean square error. Root mean square error. Yes, or the MAPE. I remember that what is this, which is the mean absolute percentage error. Yes. So these two are measures of accuracy. Please refer to my lecture, yes, on performance and evaluation if you want to get more about these two indicators of performance. I think you will need to use these indicators in your presentation. So another thing is that the trailing moving average with Windows W, yes, equal the single exponential smoothing with alpha equal to, yes, divided by the window plus 1, right? Oh, this is equal to the Windows 2 divided by alpha minus 1, right? So that is what the trailing MA, yes, it does. And what I'm trying to say is that instead of running the trailing, we can just run the exponential smoothing, which is like equivalent. Yes, they're equivalent. Right. So here we have an example of feeling the effects of alpha. Right. So here we have in alpha with 0.9. Here we have the weight that we give to alpha. Yes. And the steps into the past. Right. So we are using t minus 1, t minus 2, and t minus 3. Right. So when alpha equals 0.9, yes, right, the alpha and times 1 minus alpha equals just 0.9, yes, the previous time t minus 2 is going to give just a weight of less than 1%, and the in time t minus 3, as you can see, the weight that is going to give is less than 0.0009, which is very, very small, right? So that is what we have here, yes, in this blue line. These are the weights that you are giving to the data. So this is the weight for time t, the data today. This is the weight that you are going to give to yesterday. This is the weight that you are going to be 2 days ago. And this is the weight that you give to the observations 3 days ago. Right? So this is like a way to like visualize what are the weights that you are giving to the data when you modify alpha. So if you decrease alpha to 0.5, yes, so therefore alpha times 1 minus alpha is 0.25. Yes, so we are analyzing this time this one. 0.5, 0.25, then 0.12 or 12%, yes, to this one, and then you give to the other one 6%. And if you carry on decreasing alpha, as you can see, you are giving more weight and more weight to previous observations. Yes, when you give 0.1 to alpha, is this blue line, which is almost flat, right? So if alpha is 0.1, as you can see, we are going to give almost equal weight to the previous data, and this is equivalent to moving average, especially when alpha is very low. Right? When alpha is very low, we are doing moving average because we are going to give the same weight to all observations, and you can see that that is true here by looking the coefficients. What happened with the weight that we give to the observations. Okay, guys, I stop here. Next thing is I'm going to just illustrate a quick example for you to understand more the theoretical part. I know the theoretical part is important, but I think you are going to carry on adjusting or like understand more once we cover a quick example. So I will see you in my next video.